Hi, this is the fourth and last knowledge clip about Chapter 6, the thermodynamics of redox reactions. In this clip, we are going to talk about the concentration dependence of the cell potential, which is known as the so-called Nernst equation. We then are going to talk about the potentials that occur across biological membranes. But before we talk about these new topics, let's first apply what we've learned in the previous knowledge clip. We calculate the standard cell potential and the Gibbs free energy change for the zinc and copper redox couple. So the zinc electrode here is being oxidized to form zinc 2+. And this oxidation is given with this reaction equation, where zinc 2+ and 2 electrons are formed. The 2 electrons can now flow to the copper electrode, where they react with copper 2+ to form solid copper. An effective reaction equation is given here, where the reduction of the copper and the oxidation of the zinc are described in a single step. Now we need to find out what are the potentials of each reaction that makes together these effective reaction. So first, the oxidation. The potential of that we can find out by looking at the standard reduction potentials, which are with respect to the standard hydrogen electrode. So for zinc, we find here the reduction reaction, which is zinc 2+ reacting with 2 electrons to form zinc. However, here we have the opposite. We don't have a reduction, but we have an oxidation. But this is the reduction here. So what we do for the standard potential, we want a standard oxidation potential basically, which is the negative standard reduction potential. So from the negative here becomes a positive, right? On the other hand, for the copper, we already have a reduction reaction here, and which is exactly the reduction reaction described here in the cell, in the table, which is plus 0.34 volts. And now to obtain the cell potential, delta E standard, we just add these two potentials then to 1.1 volts. Nice. Now we know the cell potential, and now let's take a look at the free energy change of the redox reaction, which is basically describing this effective reaction here. So the standard free energy change is calculated by the amount of moles of electrons that will flow, which in this example are 2. There are 2 moles of electrons flowing. The Faraday constant, which gives the coulombs per mole, and the standard potential, which we have now determined with the help of this table. So we have 2 moles of electrons times the Faraday constant times the plus 1.1 joules per coulomb. And you see how nicely the units cancel out. The moles go, the coulombs go, and only the joules remain, which is the unit of energy. And we obtain minus 212.3 kilojoules per mole. You see the free energy change for this reaction going from copper 2+ to reduced solid copper and zinc to oxidized zinc 2+ has a negative Gibbs free energy at standard conditions, meaning it's spontaneous. Yes, we've learned that. Okay, with the free energy at standard conditions, we can now calculate the equilibrium constant K. So K is basically the ratio of the product concentrations divided by the reactant concentrations and their stoichiometric coefficients, which are 1 in both cases. You see, in this definition of K, we only take into account the ions actually, and not the solids, because the solids are actually also considered to be constant and therefore are not taken into account in the definition of the equilibrium constant. So, but we don't use actually the concentrations, but rather this nice formula that relates the free energy change to the equilibrium constant. We've determined this in chapter 5. And plugging in the negative 212 kilojoules per mole gives an equilibrium constant of positive 2 times 10 to the 37. A gigantic number. And you see that high value of K indicates that the reaction proceeds almost entirely to products. There is a very small amount of reactants still left. And it's so big because the Gibbs free energy exchange is so negative. It's a very large number. This is in kilojoules per mole, right? So again, equilibrium is far to the copper reduction, which really shows how the higher potential of the copper ions facilitates this reduction reaction. Okay, so now let's talk about the new content of this knowledge clip, which is the dependence of the cell potential on the concentration of the reactants. So here we have a generic electrochemical cell with an anode and a cathode. Oxidation of a chemical in this solution happens at the anode and is given by this generic reaction or oxidation equation, which gives us reactant A being oxidized to form the oxidized version of it C, and a certain number of moles of electrons will be liberated from this oxidation that then can flow into the cathode where the reduction takes place. That reduction with this amount of electrons now causes the chemical B being dissolved here to be reduced to form chemical D. And each of those chemicals has their respective stoichiometric coefficient in the lowercase letter for that chemical. Effectively, the two half reactions can be written with this equation, where both reactant A and reactant B then being reacted to form C and D, the reduced and the oxidized forms. And now consider this reaction to be not yet at equilibrium. Then we can write the free energy change at any reaction state with delta G. So the delta G between the current state of the reactants and the current state of the products, that free energy difference. And remember, we've written this up before. That delta G is composed of a standard Gibbs free energy part and that part that gives the concentration dependence with the reaction quotient, we called it. That reaction quotient is given by the actual concentration of products in the numerator and the reactants in the denominator with the respective stoichiometric coefficients in the exponent. So those are now not equilibrium concentrations, but the current occurring concentrations at this non-equilibrium state that can, for instance, be measured. So we also know from the previous knowledge clip that the cell potential is related to the free energy change via this equation. The negative free energy change divided by the moles of electrons that flow times the Faraday constant, which gives the coulombs per mole. And now we can just plug that equation in for the delta G here, giving a negative standard Gibbs free energy change divided by the moles and the Faraday constant, minus the second part here divided by the moles and the Faraday constant. Right? Just here the RT divided by this part. And then again here the concentration dependent part. Great. That's as simple as it is to get this concentration dependence for the cell potential. So we do know that the standard cell potential is given by the standard free energy change. And then we can plug that simply in here for the standard free energy change. Just the standard cell potential minus that concentration dependent potential. Now that is known as the Nernst equation. That gives you the dependence of the cell potential that is when it's not at equilibrium. So now that we have gotten to know to the Nernst equation, I want to show you an important application of this equation in biology, which is applied to the so-called membrane potentials. Imagine you have a biological cell like this one, where on the inside of the cell you have a high concentration of potassium cations at say 150 millimoles per liter, and on the outside you have a low concentration of around 5 millimole per liter. Now the cell is encapsulated by a lipid bilayer membrane. Inside of that membrane there are potassium channels that allow potassium to exchange between the inside and the outside. So you know, the inside has that high potassium concentration and the outside a low, and therefore there will be a concentration gradient. Since the high concentration on the inside results in a high chemical potential and a low chemical potential on the outside, you will have a transport from the high chemical potential to the low chemical potential of the potassium cations. Something really interesting happens as a result. Now imagine, those potassium ions, they also have negatively charged counter ions, right? So those negatively charged counter ions, they cannot leave the cell through the potassium channels. Only the potassium can. But the potassium really wants to go outside because of the concentration gradient. Now, when the potassium travels outside, the negative counter ions are left behind on the inside. And as a result, negative charge will build up inside of the cell, while positive charge, composed of the potassium cations, will build up on the outside. And that actually results in a voltage across the membrane. There will be a polarization across the membrane. You can imagine it's like a capacitor. Like here you have a negative electrode and here a positive electrode, and between these two there will now be a voltage difference, a difference in the electrical potential. So outside you have a high electric potential now, because you have these additional you have this positive excess charge, right? And on the inside you have a low electric potential because there's an effectively negative charge on the inside. So the voltage now begins to oppose the flow of potassium to the outside. And the potassium wants to go outside because of the concentration gradient, but the voltage that builds up will now provide an electrical force that says to the potassium ions, you cannot go outside because otherwise the polarization becomes worse. That costs energy. So that results in a so-called steady state where there's actually no more flux of potassium from the inside to the outside. And that steady state is accompanied with a so-called membrane resting potential, which is the difference between the potential on the inside minus the outside. Okay, let's zoom in on one of these potassium channels in the membrane. We have an extracellular region where there is a low potassium concentration of 5 millimoles, and the cytoplasm inside of the cell has 150 millimoles per liter. So this concentration gradient is now the driving force for the potassium ions to go from the inside to the outside. But over time, the left behind negative counter ions will create a negative excess charge inside of the cell, and the potassium ions that went outside will create a positive charge on the outside. That in turn is a polarization which results in a driving force that wants the potassium cations to go back inside, right? So you see this is this classical physics example where you have a driving force in one direction and another driving force on the opposite direction, and you know how it often goes. You then just say at equilibrium these two driving forces are the same. So we do this now in terms of free energy. The change in free energy due to the electrical work of moving 1 mole of potassium ions from the outside back to the inside is given here by delta G electric. And that is calculated with the negative Faraday constant times the membrane potential EM. Okay, so that membrane potential, what value does it have? Let's think about it. Outside of the cell is an excess of positive charge. That means it's a high potential in terms of electric potentials. And on the inside is an excess of negative charge. That means there's a low potential there. So if I subtract now a low potential value or like a high potential value from a low potential value, then I will get a negative number, right? So EM will be negative. Take a look here. That number will actually be negative for this situation. So now, if we want to move a potassium ion from the inside to the outside, then we actually have to do work now in this situation, because the free energy change for moving potassium from the inside to the outside is positive, because that number here for the membrane potential is negative, and that negative number together with the negative sign here will make this term positive, and therefore the free energy change upon moving one potassium ion or a mole of potassium ions outside is a positive number. It costs work. So you see, per definition, this formula really tells that the potential difference, electric potential difference, opposes the transport of potassiums from the inside to the outside. On the other hand, the potassium ions, they want to go to the outside because of the concentration gradient. So we can calculate the free energy change due to the concentration difference between the inside and the outside. That we call the free delta G concentration. That is just the Gibbs free energy of the outside minus the Gibbs free energy on the inside. And we have learned the Gibbs free energy, if there's constant pressure and constant temperature, and then we can calculate it with the chemical potentials. We have the chemical potential of the potassium ions at standard state plus the concentration dependent term of the chemical potential. Right? We've done that before. So since the standard concentration of potassium is usually 1 mole per liter, we can just take this natural logarithm with only the potassium concentration that is actually present either on the outside or on the inside. So we want to calculate the difference between the free energies outside minus inside. So let's do that by subtracting these two from each other. The standard chemical potentials for both of them, they will cancel out since they are the same. But the concentration dependent terms will stay, being the concentration of the potassium on the outside minus the logarithm of the concentration of the potassium on the inside here. Excellent. We can combine these two natural logarithms to 1 by building the quotient of the two of them. And now we have a nice expression for the free energy change independence of the concentration, which describes the outward driving force for the potassium ions, and equation for the free energy change due to the electric potential, which describes the inward driving force. At equilibrium, you know how it is? The sum of these free energies must be 0, right? That's always the equilibrium condition. The Gibbs free energy must be 0. And we take the individual contributions, being the one from the concentration and the second one from the electrical potential, together. Excellent. So now we can just, as easy as that, plug those here in with this equation, combine them, and we get this expression that has both of them in this subtraction. What we want to know now is the membrane potential EM, and we rearrange the resisting or the resting membrane potential at equilibrium. That's why resting is given by this formula. Resting is indicated by the star also, while here it was not necessarily at equilibrium. It's given by this formula simply. So this is a formula, it's analogous to the Nernst equation. And that's why I initially said this chapter is an important application of the Nernst equation in biology. When you take now the concentrations of 150 millimole of potassium inside and 5 millimole outside, what you get with this equation is a resting potential of negative 87 millivolts, which is a typical potential across a lipid bilayer membrane in a cell. And you do understand now where that potential comes from. The biological cell in the mitochondria works against this potential by the oxidation of NADH to propel protons against that membrane potential. It pushes the protons to the outside due to the electrochemical reaction of NADH. Now these high chemical potential protons here, they are used for the rotation of the ATP synthase membrane proteins so that they go from the high concentration to the low concentration, and the membrane potential across that membrane is effectively used for the synthesis of ATP. In summary of chapter 6, the thermodynamics of redox reactions, we've learned what electrochemical cells are and how they allow the measurement of the cell potentials with voltmeters here. Then we found that the cell potential is related to the free energy change of the redox couple reaction and also to the equilibrium constant, right? Then we just in this knowledge clip learned how the Nernst equation describes the dependence of the cell potential on the concentration of the reaction, reduction and oxidation chemicals. And last, we've learned the definition of the resting membrane potential with this equation that we just derived. Thanks so much for listening. In the next knowledge clip, we start a new chapter which will deal about reaction kinetics. See you then.